Greetings, Chem students. As you know, hopefully you know, we're studying Chapter 5 in your online text, and Chapter 5 deals with thermochemistry. And the primary concern of thermochemistry is energy. It's concerned with, more specifically, it's concerned with the energy associated with chemical reactions. And even more specifically than that, it's concerned with the quantifying, putting a number to the amount of energy, the quantity of energy associated or exchanged between a chemical reaction and the surroundings. For example, how much energy a chemical reaction will release to the surroundings as it does its thing, or how much energy a chemical reaction will absorb from the surroundings as it does its thing. Now, you know from the first law of thermodynamics, delta E is equal to Q plus W. And the first law of thermodynamics, which is illustrated on this sheet of paper, is telling us that the only way to change the quantity of energy of a system, such as a chemical reaction, is through the transfer of energy in the form of Q, heat, or W, work. Remember that Q is the amount of energy exchange between a system and the surroundings through the random motion of particles. And work is the energy exchange between a system, a chemical reaction, and the surroundings through coordinated motion. So let's illustrate that with this little box of particles. Energy is due to the random chaotic motion of the particles that make up the body, the piece of matter, the system. And remember that temperature is a measure of the average kinetic energy of particles. So at low temperatures, particles have motion, and that's their kinetic energy. But as the temperature increases, their kinetic energy, their energy of motion increases. Their temperature goes up. So temperature is a measure of the average kinetic energy due to this random chaotic motion. And that is how heat energy is exchanged. Heat energy is the exchange between a system and the surroundings through the collision of these particles. These fast-moving particles collide with other particles and in the process transfer a portion of their kinetic energy. That's heat energy exchange. That's Q in our equation. Now, work is energy that's exchanged between a system and the surroundings. The only other way that energy can be exchanged between a system and the surroundings, remember the first way is heat, the second way is work, and work is energy exchange as well, but not through the random chaotic motion of particles, but through the coordinated, organized motion of particles, such as this. And this is showing all the particles moving in the same direction at the same time at the same speed. That's not chaotic or random, that's organized, coordinated, synchronized motion of energy transfer, and that's what work is. So, a fascinating thing about the relationship between heat and work is whenever heat energy is exchanged, whenever heat is on the move, it's possible, if we're clever enough, to take a portion of that heat and convert it into work energy. And that's what these machines do that we have here on my desk. These are called heat engines. And here's the first one. It's a Stirling engine. It's just a particular kind of design of a heat engine. We have a chemical reaction taking place there. We're combusting alcohol. So the alcohol combines with oxygen, undergoes an exothermic chemical reaction, releasing heat. And this is the heat energy that's absorbed by the engine. And as that heat energy flows into the engine with this clever design takes a portion of that heat and converts it into work, organized, coordinated motion, like that. So as heat's flowing in, the design of this engine is such that it can divert a small portion of that heat energy exchange, convert it into work energy. And notice that all the molecules, all the atoms of this rotating wheel here are moving in the same direction at the same time. And that's coordinated, organized motion. That's work. And we can do wonderful things with that kind of work. And it was actually the invention of the steam engine back in the 1700s. This is not a steam engine, but the steam engines are heat engines that created or initiated the Industrial Revolution in the 1700s. So that's a heat engine. This is also a heat engine, a Stirling engine. And what's fascinating, another fascinating aspect about the relationship between heat and work is that we don't even need to have a chemical reaction necessarily creating the heat to get the work out of an engine. Here I have hot water in this styrofoam cup. It was nearly boiling. And this is our Stirling engine, our heat engine. Now remember that heat always flows from hot to cold. And the hot body is the hot water in this cup. The cold body is the air outside of the cup. So the heat is flowing out of that cup, but it has to flow through the engine to get to the cooler outside. And as it does so, this engine will convert a portion of that heat into work. And here we have our rotating wheel again. All the atoms of the wheel are turning the same direction at the same time with the same speed. And that's a heat engine, converting heat, a portion of the heat, into work. And now notice that the direction of this rotation of this wheel is clockwise, losing heat there. But all you have to have is a temperature difference to create the heat flow. And whenever we have heat flow, we can, in theory, convert a portion of that into work energy. So now I'm filling this cup with liquid nitrogen. And liquid nitrogen is about minus 200 degrees centigrade, and the surrounding air here is about 20 degrees C. So now I'm going to put this engine in contact with the very cold body. Now, which direction is the heat energy going to be flowing? Now the hot body is the surrounding air, and the cold body is the liquid nitrogen in here. So now the heat is going in this direction. And as that heat energy flows through the heat engine, the engine is able to, through a clever design, to take a portion of that and convert it into work, hopefully. Let's make it a little colder, perhaps. Get a little more of this in there. Oops. Okay. And come on, baby. Or the heat engine was hot from when I had it in contact with the boiling water. So it's still got that residual heat that's offsetting this cold, the heat transfer from the cold, from the hot to the cold in this device, in this situation. Come on. I wish I knew how to pause the camera, because eventually it's going to get cold enough to do that.